Hello, hello. Can you hear me?
Ah, yes, it works now. I
Excellent.
don't know.
How?
It's some problem here. You have to reconnect and then it works like every time. I don't know why. I'm
Yeah,
fine, thanks. How are you?
good, good. What's your name, please?
My name is Daniel.
Daniel. My name is Patrick.
Nice to meet you, Patrick.
Nice to meet you too. Um, I
So,
think this is
it,
this question for myself, right?
yes, it's my turn to be an interviewer, and they swap it problem, so I also see it for the first time. So let's
Okay,
try to do it. Okay, so you're given an array of integers where each element is at most k
but
places away from
but for
its
this
sorted.
question, I think you are the interviewer, right?
Yes, for this question, I am the interviewer,
And
and you
then
are the
after that,
interview.
after that we swap.
Yes, of course. You can read it yourself if it's more convenient. Like,
hmm
okay.
Oh, looks like this is like about sorting, right?
Yes.
Given the okay, at most k pieces away from its sorted position. Wow.
Uh-huh.
Okay. Okay, let me analyze the question here. So we have like a 1, 4, 5, 2, 3, 7. So we
Hmm.
have the array like this. Okay. Wow. I have to
Okay.
think about how to do it. Um, but it's interesting problem. So we have the array like this. So and then also k and k being, let me see, at most k places away from its sorted position. The goal the goal is looks like this.
Hmm.
And let me see. Well, how many places away from its sorted? So the first one is going to be exactly what we need. So it's 0. So the next one is going to be 2, and the next one is still 2. I'm just taking difference between the our starting point. This is our
Hmm.
starting point, and this is our goal. And then and this is how much it takes for us to get to uh, where we want to go, where we want to be, and from where we are right now. And
Hmm.
then okay, so all the distance is um, 2. Oh, I can let me call it distance. It's more descriptive of a name. So yeah, so I'm taking difference between the two. Absolutely. I don't need to take absolute difference. The first one is going to be -2. Well, let's take absolute difference. I'm going to take difference. So 2 2, etc. So the rest is pretty similar. And then this one's plus 2,
Mm-hmm.
and then this one is also plus 2, and then this one is minus 1, and this one is minus 1, and then we have the rest. So it's very similar concept. So basically we are for this case we are k is 2, right? K is 2, so we are two places away from where we want to go.
Mm-hmm.
Okay, so looks like 1, 2, 3, 4. Okay. Okay, interesting. How can we use this information? Use the K. Yeah, if let's say if I'm not given the number K, we can use merge sort or quick sort,
Mm-hmm.
right? But now I have one more piece of information, which is the K, which I
Yes.
know that my goal is gonna be very is only within that range of the neighbors.
Yeah, that's right. So you have kind of limited range of neighbors to do your sorting.
Let me think. Oh yeah, I'm pretty stuck because I'm thinking about like
Oh.
in here, because let's say if the starting point and then we look at the first element and then we know that um, there's no left room to go. That's why it's not going to be here, but it could be the goal could be in here or in here,
Mm-hmm.
right? So and then the same idea in here. So and the four can be, I mean the goal will be can be in here, here or here. So everything is possible. Or it can stay where it is right now. Um, so
Mm.
it has a range to go.
Yeah,
Um,
and this range it kind of slides through this array, right?
yes, the range slides through the array. Yeah.
Mm-hmm.
So the first range is gonna be like this shadow,
Mm-hmm.
and then we have the range like this, and then the range like this, and but how does that help me though?
And after that, what the range will look like?
After that, the window will shift like this.
Okay, yes, that's right. So kind of sliding window fashion. Maybe could you try to think of what can we do, like knowing that it's this sliding window kind of task.
Sliding window. Let me think. Um, this two. Yeah, because I'm thinking, like if the window looks like this, and let's say if we're looking at one right now, it looks like this, and we know that
Mhm.
the smallest spot is here, so we take that, and then in here, um, Um, yeah, in here, and then I know that the second smallest number is, yeah,
Like, uh, try to think maybe of on the very first iteration, we have this kind of sliding window of three elements. And what would be the first element? So, how do we find the element that should go on the first position, given this sliding window?
it should be the smallest one.
Yeah, it should be the smallest one. That's true. What is the asymptotic of finding the? How could you efficiently find the smallest one?
How can I efficiently find the smallest one? Yeah, so this is kind of, yeah, kind of sorted. Well, one quick way I can think of is to be binary search.
Yeah, but they are not actually sorted because they're swapped. No, like in general, the task, as you maybe notice, is to find the minimum over sliding window, right?
Mm-hmm.
So you have kind of a sliding window that in all the first iterations it kind of a little bit inflates, but in general it's sliding window. And on each iteration you have to find the minimum. So what is the most efficient way to do it?
Oh, so each one of the sliding window we need to find a minimum. That's what you said.
Yes, yes, actually that is what we need here.
Oh, okay, okay. Each sliding window that. So we can have like a running minimum. So for example, when we are at this window, the minimum is gonna
Mhm,
be the minimum of these three, and then when we
mhm.
move to this yeah, this window, and then the minimum will be, well, in here we already, oh, okay, I kind of see where you're going with this. So because when the window is like this, right, the minimum is going to be one, and then we place it and then swap it if it's not in the
Mhm.
correct place. Yeah, in this case we don't need to swap it. So and then we will move on to here, right, and then find the minimum, which is two, and then two, and then the four swap with the two.
Yes, but actually, I guess that we are not required to actually swap some elements, but we are required to return this sorted array. So you can just have an empty array and put their minimums on each iteration. Like on the first
Oh,
iteration,
okay.
you find that minimum is one, and we put it to result. Then the second iteration, we move forward and we find minimum two and put it into result. And the question is how to efficiently to find these minimums.
Okay. Um, okay, I see your point now. Well, I mentioned about binary search, but you said this is not sorted, so it's not useful here. And
No, it's
and then now this is for example in this window, and then we found a minimum, and then we don't care about the one anymore. I mean the first spot anymore, and then we move on, and then the window like
yes.
this, and then we find another minimum, and in here, let's say 452, the minimum is two, and the
Mhm,
efficient way, a not efficient way, just take the mean function across these three.
mhm.
However, we have already done some work right here, right? So, when we were in this this sliding window, and then we know that the minimum is 1, and then for this window, and then we can, let me think, it's going to be between, because this window the minimum is 1, and this window is going to, let me think, no, it doesn't work this way.
So actually, maybe think of some data structures that kind of support easily finding minimums.
Heap.
Yes.
Yeah, it's going to be heap, because heap is going to be all log n for each of a pop. And then log n is log k here.
Sorry, didn't catch you.
Because the heap, the mean heap, when we use the mean heap to find the minimum, it's going to be big O of a log k to find the minimum. So okay, that makes sense.
Actually, it will be log k to pop out the minimum, not to find, or even maybe to insert. To pop, it will be constant. The insertion in the heap will be log k. That's right.
Right.
So try to think of how we can use it here.
So when we sliding the window, and then for example at this window, and then we will have this all into element, and then we pop the smallest one, which is 1, and then move on to the next window. And then we know that then we pop the other one, which is 2, and then we can still move on and then to the next window, which is this guy, and this guy, and then keep going until we keep popping the smallest one, and then when we pop it, and then we will append it to the a new array.
Yeah. Okay. What is the time complexity of this approach?
The time complexity is going to be, as you mentioned, the inserting is going to be big over log k, and then we have to do n time, right? Almost n time, right? And then because we have to basically scan it through the entire array, so the time complexity is going to be n log k.
Yeah, that's right. And what about the space complexity?
So space is going to be, because we need a heap, so it takes k space, and it's going to be big of k. If we don't care about the n array also takes some space as well.
Yeah, that's right. It's like O of k and plus the space of the final array. So probably let's write some code.
Okay, sounds good. And thank you so much for helping me out along the way to figure this out. So
you're very welcome.
So I'm gonna use a sliding window approach. So the first window is gonna be like this. So the window is gonna be, so of course we need we need to use a heap. We need to heap queue. Queue. For I think. So I'm gonna look at the array, some sort of a range. So in index in range of, and let's think. Oh yeah, my starting point is gonna be, let's say 0, 1, and 2. 2 is the k plus 1. This is my starting point. The end point is gonna be I think the length of array. The length of array. It's gonna be the length of array, because the last one is not included. Good. And also this is gonna be the end of the range. I call it n, and then I have the start of the range, and the start of the range is equal to the end. I think. Let's see if I'm get this number. This number minus k minus 2k minus 2k. Well, I need to take a max function over this, and also 0 because it cannot go beyond the left hand side. So now I found the range. So the range is now is going to be the sliding window now is going to be the starting point and the end point inclusive. And now I'm ready to do use the heap queue. So heap queue dot heapify. I think. Yeah, heapify is to heap the. Let me think. Yeah, so because the first one is I need to do heapify, but I don't need to do heapify anymore afterward. I don't.
Yes,
I don't.
right. But I think you need to do heapify only once, and then you have just a heap, and you do only push and pop.
Yes, exactly. Let me think. So heapify at the beginning. Let me think. So the way I think a good way to do this is, let me think. Just arrange like this at the beginning, and I think maybe easier to do like something like this. So to this array. Yeah, I'm go with this. So I'm gonna take the first k element, and then do a heap.heapify, and I don't need to worry about the edge case at the beginning as well. Did I spell it right? HEAP heapify.
There is single P, I think.
Single P. Okay, great. Thank you. So now I have the the running heap. This is a starting point, which is the first k element 0, 1, 2, k plus 1 maybe.
Yeah,
0, 1, 2. Yeah, k plus 1 because the first range right here. And then what I'm gonna do is I have also the answer array. Answer is gonna be empty array, and then the first answer is gonna be I think I can do something like this. Answer equal to an array, and then do heap q or heap pop. Yeah, heap pop. Q, and then running heap. So the first one is called pop off. So it's good. And then now already at this range, and then I'm gonna move on to the next window. The next window is gonna be like this, and it's gonna be, the starting point is gonna be 0, 1, 2. Oh, the end point. The first end point is gonna be 0, 1, 2, and 3. 0, 1, 2, and 3. So it's correct. It's k plus 1. Yeah, the starting point is k plus 1. That's correct. And then the endpoint is going to be length array. Yeah, exactly. So I mean the endpoint. Hold on, but the starting point might not be right though. The n minus 2k minus 2k. Oh, the starting point. You think?
But why do you need this part starting point? Like the only you have to do now is to push and to pop, to push and to pop, and that's all.
Oh, oh, right. Yeah, you're right. So when I this window, yeah, when I move on, yeah, you're right. So yeah, I was overthinking. So yeah, you're right. So in the index of yeah, first window like this, and then second window is like this. Um, and then it's gonna be yeah the next one. Yeah, you're right. Yeah. So he queued up, he push, and then pushing the latest member IDX, no
Mm-hmm.
INX, and then immediately what we can do is to append the heap, like come out of it. Queued up hip hop. Yeah, I think that should be it. Uh,
Uh, Check it at the very end. You have something left in your heap.
oh, right. Yeah, you're right. So, yeah, exactly. Um, so I'm gonna clean it up.
Mm.
While there's something, I just more to be more explicit.
Ah,
While there's something in the heap, and then we keep popping up.
yes, that's so. Yeah, seems to me that it works. It will work. We can run some tests to check it.
Yeah. Now,
Run.
let, we have a few minutes. I'm gonna do some dry run to make sure it works. So let's say if we have I'm gonna have a very short example. Let's say uh, 0, 2, and 1, and then
Mm-hmm.
the k is let's say 2.
Okay,
Yeah, k is actually 1 in here.
maybe one. Yes, one is better here.
Yeah, k is 1, and then let's say the running heap at the beginning. So it's gonna be the first two elements. So it's gonna be like this.
Mm-hmm.
Um, and then he pop. So we pop the zeros, so it works. And then
Mm-hmm.
the k plus 1 is 0, 1. Uh,
K
yeah,
plus one
0
is
and 1,
two
2. So the
actually.
last one, yeah, take the last one and then push it.
Mm-hmm.
And then yeah, so it could become 2 and 1, and then pop the smaller one, which is 1. And then yeah, so it should
Mm-hmm.
work based on this example. Let's run it. Undefined. Okay.
Undefined heap argument must be a list. Probably this array slicing didn't work. Mhm. I think that maybe you should add something like this
Oh,
in
maybe.
case,
Oh, I
but
think. Oh
but
no, I think maybe you can use the list like this. I think
or list. But I am
it should
thinking
be a
that
list though, right?
yes, it should. It's some weird case with the you see input is one and zero, so you pass here, but you pass here an empty list.
Oh,
Maybe
there's an edge case.
Yeah, maybe there should be some explicit check on the
Yeah,
on
for
K.
so if the length of the array is less than or equal to 0, or not 0, 1, just return. uh,
Probably something wrong with the Hipify. I don't know. Just let me array couple K plus 1. Uh, Let me check. I have right now no ideas why it doesn't work. We have some array. We have K plus 1. Phi. Oh, it, just what is input 1 0 and 1.
oh, I think I kind of know why. Because the k is 1, and then k plus 1 is 2. K plus 1 is
Okay,
2, so
so
that's
it's
the.
me. I'm thinking of maybe in there is a problem in heap push that arguments are swapped. Push push heap item. No, that's right. Running heap. Okay, let's just Google it. Heap argument must be list. I don't know. It should work even for list.
Yeah,
For
I think the edge case here is that, so let's say if I'm gonna try, if it doesn't work, I'm okay. Okay, I'm gonna move on. I think the edge case here is that if the k is bigger than the length of the array, it's possible, right? Let's say if the in this case the length of the array is 2. Let's say k is 1. Um,
mm,
but if the k is exactly, let's say exactly equal to the length of the array, and yeah, so in this case, is the running heap is gonna be the entire array. But it doesn't solve this problem though. The k is 1, the length is 2, and then k plus 1 is 2. Yeah, so it should work though. Yeah.
and it's does it work now? I'm just trying to reproduce it locally, but indentation. I have indentation errors because of these two spaces indent. Okay. Mm. Ah, yes. I. But no. Let me
Well,
check.
it's okay. I can go figure out myself afterward.
Hip hop. Released. Released. Ah, yes. The or uh, okay, okay. Hippify actually doesn't return anything. Hippify is in place
Ah,
operation. So yes, the error is much simpler than we thought. You
oh,
just you just modify the array in place when you do this hippify.
okay. So if that's the case, is I think the way, okay, I remember it now. Yeah, you're right. So we can make a copy of that array then.
Yes,
Um,
but you yes, actually you need to make a copy and then to use the hippify.
it's gonna be like this. Yeah, I
Yes,
remember that now as well.
yeah, and
Um,
I think it should work now. Yes,
Perfect,
yes, it works. Okay.
wonderful. Thank you.
Okay,
Now
you're welcome.
let's swap the role, and then I'll be the
Yes,
interviewer. You'll be the interviewee.
yes, let's solve the roles. So
Oops. Here.
array index and element equality. Given a sorted array of distinct integers, write a function index equals value search that returns the lowest index I for which array equals I. Oh, pardon, some messaging. Array equals I. Return minus one if there is no such index. Analyze time and space complexities of your solution and explain its correctness. Okay, so we have something sorted and we want to find the lower boundary. Seems like it's a very kind of common task on the binary search. And what are we going to do here is we're going to find the midpoint of array and check if this midpoint is less or greater than our target value. And if the midpoint is greater, then we go to the left. And if midpoint is less, then we go to the right. And then we do the same thing kind of recursively. And at the very end, we arrive to our destination. The only probably here thing is to handle this lowest index, not like any index, but the lowest index. And what we will do is it kind of depends on, we will have two indexes, like we'll not do recursion, we'll have two indexes. The first will point before the end, before the beginning of the array. The last will point after the end of the array. Then we will check the mid, and then these indexes will come closer and closer and closer and closer. And in some point of time, we'll stop and we will return probably the left index. So I think it should work like this. It will be in logarithmic time and in constant space, because we will not allocate like anything except these two pointers.
Can you walk me through again your thought process? Like how does it to narrow down the the spot that you want to look for?
So I can write something here. So we will have, say we have this array. We will have one pointer here another pointer here. And we begin our iteration process with finding the middle between these pointers. The middle is, will point to 0, I guess. Okay, we found the middle, and we are comparing this middle to our target element, which is 2 in this. Let me just target this 2. We compare this middle to R2. We realize that middle is less than 2, then we can move this left pointer to this middle pointer. And we arrive to this situation, we find the new middle. The new middle will be, I guess, something like 5. We
Yeah,
check.
just a reminder to you, this target is different for each of the position. So for example, the target for this first guy is going to be 0 because we're looking at the the index to be the same as the value. So you don't
Just
have,
sorry, maybe given a sort of this intention.
yeah, read one more time more carefully.
Ah, yes, write a function index equals value that returns lowest index for which for which index equals. Okay. I was trying to solve a different task. Okay, so we want to find the index and there is no target actually. There is no target. We just want to find the position. Okay. The position where index equals the value. So naive approach is, of course, to iterate through the entire array. It will be linear, but probably we can do better. And this better will be inspired again by the binary search. How we could use binary search here is like probably we will go to the middle and kind of check. Say this middle element is 0. Is its index greater or less than the value? And there are three cases. If index is equal to value and we have distinct integers, that means that this is the only solution. Just let me think. Is there any case where we can have multiple solutions? Seems like no, because given the array elements are distinct and the indexes are distinct, there could be just a single place with an equality. No. Not just if we can, there can be like array of 0, 1, 2, 3, and everywhere will be
There
equality.
you go. Exactly.
Yes.
Perfect.
Okay. So returning to our binary search idea, we see this 0 in the middle.
And then for that case, you need to return the smallest one.
Yes. Thank you. I got it now. So this 0, there are three cases. If this 0 is greater than its index, given the array is sorted, there is no sense to go right. So we can be sure that on the right, every value will be greater than the index. So we will go left. If 0 is less than its index, then what is then? Can we go right if 0 is less than its index? Let me just think. 0 has some index zero is a bad example. We have, let's say there is 3 and 4. It's
Yeah.
kind of
Let me give you a small help. Very small
uh
help. You are thinking along the right direction, and I want to make your thinking a bit easier. Think about the difference between where you are, the value, and the index. So you take the difference, and then you can see how do you want to reach to your goal. Yeah,
yeah,
and
thank
you're
you.
thinking about the right way. They compare or which one's bigger and smaller, but actually you can take difference. You can immediately see that. Um,
Mm,
yeah, that helped me
mm.
anyways. Yeah,
Yeah, thank you very much. So the difference, uh, if the initial array is kind of, the difference is very good in sense that we need a zero difference. It's kind of easy to understand. But do we have a guarantee that the array of differences will be sorted? I think that yes, or no, or yes. um, is it
try it.
possible?
Yeah, try. I mean, have an example and try it. It's you see the example like this is like this, right? This is an example,
Yeah, and this
and then
this will be
exactly you can
zero,
just take a
one,
difference. You
two,
can see exactly is that uh, increasing or
one,
is it decreasing, and
two,
you can see immediately.
three. So the difference will be, I'll subtract this from this, say, so it will be -8, -1, 0, 2. Seems like it is increasing, and could it ever be decreasing? Like if we had here, for example, 3, then we'll have 0 here. So probably it is at least not decreasing array.
Exactly. There you go. Perfect.
Yeah, yeah, because every next element is at least one greater than the previous one in both arrays. So okay,
Exactly.
we have the array of differences, and now the problem is actually the binary search. So we need to find the first occurrence of 0, which we'll do by this pointer fashion. Kind of we initialize pointers, find the middle element, and so on until reach the result.
Mhm. I think you're good to go. And um, think about it, whether you need this array or not.
Uh, Actually, I don't really need to materialize this array because I can calculate these numbers like on the fly, because I will have the indexes and I will
Mhm.
have the initial array. So it doesn't make sense to use extra memory.
Yeah. So what's the yeah? You are really ready. You are almost ready to go. But I'm gonna ask you, what's the time and space complexity before you code it up?
Okay, the time is logarithm, and space complexity is constant because we just need to store two numbers actually. And
Perfect. Yeah. Please code it up.
okay, let's get started. So let's initialize the pointers. What goes here? And what are we trying to do? That's why left is less than right. we are going to find middle element. Array length is not so big, so we can just stop thinking of these integer overflows. And we have the mid element, and there are three cases, as I said. If now I have to pay my attention, so mid is the index minus array mid, which is the value. If it is equal to 0, it's actually greater or equal to 0, then we will go left. So update this, and otherwise we will go here, and somewhere here we should make +1. Just let me see. I think here we should go +1 to yeah, if mid is less, then it's not interesting for us, and we just increase it. And if mid is 0, it could be on the right. And at the very end, should we return? No, we should return this index or -1 if we didn't find. So I think it should be like this. So we will return the first 0 element because our right will be the element with where this is greater or equal to 0, and the left will be yes, it will actually be equal to right at the end of the iteration, and we are just checking this thing. And I think I have to get this for some edge cases. For example, if the array is very small. So let me check it on this simple example here. So we have this example, and we have two. Left will be -1, right will be 4. Mid will be -1 plus 4 divided by 2. will be 1. 1 is here. So 1 minus array mid 0 is greater. It's 1 minus array mid. Probably I swapped it. So 0 minus 1 is greater than 0 is false, and it means that our left goes to mid plus 1, which is 2. Okay, and then again, here we go. Here is 2 plus 4 divided by 2, which is 3. 3 is the last element. If array mid, if this is greater than 0 and it's greater than 0, then we have 3. We have some problem here. We have some problem here. Hell, binary search. I should have written it very good. So
where did you get stuck? I think your code is. I mean, your logic makes sense to me.
sorry, the logic?
The logic makes sense to me.
Yes, but it's somewhat not absolutely working now. So here we move this. And then we'll update and go. Probably. I don't know, probably like this. So okay, I have to review my binary search. Some problems here.
Yeah, no problem. I mean, I'm not. Yeah, so yeah, I would recommend you to take a review on the binary research. But some tips I can give it to you. Some feedback, at least.
Okay.
And yeah, so for example, I mean the way that I would code binary research is that if we so the first those are just the left pointer and the right pointer. So this is gonna be I would do like a 0 and -1, and then I could look through all the indexes. And then what I would do is I would, but in my solution, I would have like a difference variable. So I have exactly what you did, like this. And then I would think about, if you exactly right. You are exactly right. So if there are 3 cases, if the difference is exactly 0, right, and then you do something, right. So and then if the difference is less than 0, and then you would do other things. And then if I mean, for this, it actually helped me to organize my approach. Like I don't need to worry about like, maybe I have to go, if these 2 cases, it handles like this, right? So it's sometimes more easier for me to, my thinking process, easy for me to follow. For example, if the difference is 0, and then I know I have a answer somewhere here, I saw that the answer is 0 and none, right? So I have an answer of something, right? I have to update my answer because I found a local answer already. but I can keep search, right? Because it may not be, maybe it's still too big. So, and then I can go left, right? The way that I go left is the right equal to mid -1, right? So I go left, and also I update the answer, which is in this case gonna be mid, right? And then if the difference is too big, right? It's too big. I also go left. So I go like this. And if the difference is too small, I go right, right? So go right is gonna be left equal to mid +1. So I don't need to worry about those edge cases at the end because it's a bit handled right here. And at the end, I will return the answer if the answer is not none. Otherwise, it's -1, and I know it's gonna be -1 possible. So this is my solution. I'm hope that can help you to. I mean, this is my way. Oh, it's else if, and also else here, and actually this is the case that we are handling.
Yeah, okay, that makes sense.
Yeah. So this is my way to tackle this. But your thinking process, your logic is really well, and your time complexity and space complexity analyzed really well. But just need some polish on binary search for coding.
Yeah. Thank you very much.
Okay. Yeah, and thank you as well, and to be my interviewer. I really enjoy working with you today.
Thank you very much. Thank you.
And good luck to your upcoming interviews.
Good luck for you too.
Bye-bye.
Thank
Have
you.
a nice day.
Have a nice day. Bye-bye.